Welcome to our last unit of the year. Today I'm going to talk to you about electrical charges, how things can get charged, and electrical forces. So let's get started. Electrical charges have two states, positive and negative. You're probably familiar with those. Well, in physics, the unit for charge is a coulomb, and we're going to abbreviate that with a capital C, so that'll be our unit. And then in the equations, the variable that we use to represent a charge is a lowercase q. Now, a couple of things you'll need to remember. Charges can be separated, they're not created, and it's the electrons that can be removed from or added to the atoms. And then we also have this word right here, electrostatics, and its definition is the study of electric charges that can be collected and held in one place. You're probably familiar if you get a little electric shock, that would be from electrostatics. We're going to study charges that can be collected and held, and then when they get released, you feel that in the form of a shock. Take a moment to fill in this chart. These are numbers that will be provided for you, but I wanted them in your notes in one place so that it's easier for you when you go to do your quest problems. So we have the charge of electron, proton, and neutron. Those are right here. The mass of each of those three things, and then some notation that you might see if you didn't want to write out the words electron, proton, and neutron. And then the other important thing for you to remember is that like charges repel and opposite charges attract. So go ahead and pause the video if you need more time to fill those in. Now, I don't know if you've had a chance yet to play with the electricity kits, but one of the activities that I'd like for you to do is test different objects and see if they are a conductor or an insulator. Conductors are materials that allow charges to move about easily. Typically, those are going to be metals. So in our electricity kits, if you hook up a light bulb and you make a conductor part of that loop, then you'll still be able to see a light bulb light up. Insulators, on the other hand, are materials that do not allow the charges to move easily. So those charges are going to stay in one place, and you'll see from our electricity kits that we need a flow of charges in order to have a continuous circuit and make our light bulbs light up. So if we put something like a piece of plastic or some glass or a cloth, something like that, in our circuit, then that's going to stop that flow of charges and our light bulbs will no longer light. There are different ways that you can charge an object. The first one is charging by conduction, and you can remember conduction and contact start with similar sounds. So what would happen is you take a neutral body, so something that's not positive or negatively charged in either way, and you touch it with something that is charged. So there's physically contact, and those charges transfer from one to another. So I have a little picture here for you if you wanted to pause and take a moment and look through that. The other way that we can charge objects is by induction, and sometimes you'll see this called the separation of charge. And so what happens is we take a charged object and we bring it near an uncharged one or a neutral one. There's no physical contact, and the charges do not transfer from one to the other, so they just separate within the different objects. And also, if you want to pause the video and kind of look through a diagram, I have an example for you, and then I will probably post an additional PowerPoint on Google Classroom to get you a better idea of some more examples for electrostatics. Now, the last thing we're going to talk about today has to do with electrical forces. So I want you to think about the dynamics chapter. I think it was the third chapter that we did when we added our forces together and put things in equilibrium. Those same concepts are going to come up again, except now we will apply those forces to electrical scenarios. So we have a very important law. It's called Coulomb's law, and this represents the force between any two charges that are separated by some distance. For now, I just want you to get the formula down. We are going to do example problems together in class. So for today, I just want you to concentrate on filling in your notes and getting the basics. So an electrical force, it's represented with an F, just like our other forces. We have a constant, this is K, and its value is 9 times 10 to the 9th, newtons times meter squared over coulomb squared. This is a number that will be provided for you. And then our Q's, remember, represent a charge. So we would have charge number 1 and charge number 2. So those are subscripts. And then they are separated by some distance. And that distance does get squared. So this is what's called an inverse square law, because the force varies inversely with the square of the distance between the charges. Because charges can be positive or negative, When we multiply those two together, if the product turns out to be negative, that would be an attractive force because we would have one positive and one negative, and opposites attract. And then if that product of our two charges were to be positive, that would indicate a repulsive force. So we could have two protons, so two positive numbers multiplied give you a positive number, or we could have two electrons, and two negative numbers multiplied also would give you a positive number. And like charges are going to repel. So our superposition principle is going to relate back to our dynamics chapter when we talked about resultant forces. So you can review that if you need to go over Pythagorean theorem and components. You should have those notes in a previous chapter. So for electrical charges in Coulomb's law, if we have two or more charges that are present, we want to find the resultant force. And then if the forces are at various angles to each other, we do have to break that down into components, and then we can use the Pythagorean theorem to find the total force, just like we did when we studied dynamics. I have a little problem-solving strategy for you to kind of help break this down into steps. So first, you would want to identify your variables. Then we're going to determine the direction of the forces based on if the charges are positive or negative. So are they going to attract or repel each other? That'll help give us a direction. And then the magnitude, remember that's the size of the forces, will be calculated with Coulomb's law. From there, we can look at our horizontal and vertical components of each force if they are at various angles to each other. Then we can calculate the magnitude of the total force in the horizontal direction and in the vertical direction. This would give us the two legs of a right triangle, and we can then use Pythagorean theorem to find the resultant force. From there, don't forget you would also want to find an angle, so we could use some trig function. You would take the inverse of that function to find the angle of our resultant force. So on this slide, you don't need to write anything down. I was just setting up an example problem, and I do want to go over that in person with you, so you can skip this problem and we will go over that together when I see you in class. The last little bit of notes I would like for you to write down is about equilibrium. Now you've actually had this before when we talked about forces, but now we're going to apply them to electrical charges. So according to Newton's first law, an object is in equilibrium if the net external force acting on the body is zero. So that means we want to add up all of our forces together. If they all cancel out and equal zero, then our object will be in equilibrium. For electrostatics, this means that we would have an equilibrium position of a charge. That is the location at which the net electric force on that charge is going to be zero. So in order to find this location, we would have to find the position at which the electric force from one charge is equal and opposite to the electric force from another charge. And then to do this, we can set the forces found by Coulomb's law equal to each other, and then we're going to have a little bit of algebraic manipulation to solve for the distance between either charge and determine the equilibrium position. So I realize you do have another example problem in your notes. Just hang on to that one. We are going to go over it together in class and work through all the steps so that you can get a chance to ask questions if there's something that you don't understand. That's it for today, and I will see you in class.